Alright, in this video we're going to look at some examples of comparison tests. Now, comparison test compares to something. So what do we have to compare to? At the moment, we have the p-series, of course, and I guess we know integral tests for a few things, and obviously the geometric series. Or if we could compare to something that we know diverges by the nth term test, those are options we have. There are two kinds of comparison tests that we're interested in. The first is what is called the direct comparison test, or DCT. The direct comparison test compares two series with positive terms, an and bn. And here's the deal. If bn is convergent and an is less than bn, then this is convergent. So in other words, if you can show a larger series of positive terms converges, then a smaller series also built from positive terms will also converge. On the flip side, if you can show a series of positive terms bn is divergent, and you have another series which term by term is larger than that divergent series terms, then the larger series is, of course, divergent. So intuitively, this comparison test makes a lot of sense. Let's see how we actually put it into practice. All right. I have to get my fingers to work here. So example 1. Here we have a series with positive term 1 over 10 plus 3 to the n, and this is less than that y. Well, if we make the denominator smaller, it makes the fraction larger, right? So that's an important inequality idea if you didn't know already. You know, if we want to make a fraction larger, we make the denominator smaller. So there you have it. This is less than that, but of course this gives us a geometric series that converges to that, which I suppose is 3/2. So by direct comparison, we find that this converges again. So by direct comparison to the geometric series, this one, we found that that converges. So I would caution you, it's better to say the series converges. It would be not as good, and sometimes wrong, to say by direct comparison we find it converges. The question is, what is it? Now you could say, well, it's obvious that I'm talking about this, but you know, it's just better to be clear and not use a pronoun here. Say we find this series converges. Or you could give a label to this, call this thing S, and then say we find S converges. But I would strongly discourage the use of pronouns, such as it, especially it. Alright, anyway. In fact, what do I have to say here? In fact, in case 1, this is less than that, and we also obtain some estimate. So in particular, for example 1, I can tell you more than it converges. I can actually tell you that because the larger convergent series converges to 3/2. Did I say 2/3? I forgot what I said. Well, apparently 3/2, right? 1 over 1 minus 2/3 is 3/2. So by comparison, I actually learned that this series converges to some value less than 3/2. It's also bounded below by 0 because the sum of positive things is positive. Or it doesn't exist as a real number. Alright, anyway. Example 2. Moving along here. In example 2, we have n over n squared minus 4. Now, I'll tell you my intuition here. When I look at something like this, I ignore the 4 is what you do. It's sort of just to gain intuition, just ignore the 4. And what do you got? You got n over n squared, right? Oh no, n over n squared, that's 1 over n. We know that's the, excuse me, p equals 1 divergent series if we ignore the 4. And so this doesn't look good for this one. Doesn't look good. So I suspect that this is going to diverge. So I want to compare it to something larger. And in fact, the p equals 1 series is a good choice. So to make this fraction smaller, I make the denominator larger. See, n squared minus 4 is smaller than n squared. That makes this fraction smaller than that one. And then, of course, n over n squared is equal to 1 over n. By the way, the reason that we started this one at 3 is because if you plug in 2, it's just, you get division by 0. So, since the sum n equals 3 to infinity of 1 over n diverges, it's the tail of the p equals 1 series, we find that this sum n equals 3 to infinity of n over n squared minus 4 diverges by direct comparison test. All right? So the direct comparison test is sometimes useful, but there is another test, namely the limit comparison test. Let's talk about that. The limit comparison test involves a limit. And limit comparison test, I think students tend to like the limit comparison test a little bit more because, in contrast with the direct comparison test, limit comparison test doesn't require you to derive or at least state an inequality between the given series. So here we go. We've got two series of positive terms. Suppose that the limit of their quotient is c, where c is a finite number and a positive number. Then either both series converge or both diverge. This is the limit comparison test. So a lot of times this is, again, you notice what you don't have to show that an is less than bn or bn is less than an, in contrast to the direct comparison test, right? So here's an example of limit comparison test. So, by the way, proofs of these should be found in your textbook, and it would be healthy for you to try to look at the proof of these to understand why these are true, but I'm going to mostly focus on examples here in these videos at the moment. Okay, so this, ignoring the minus 1, is essentially p equals 1/2, so we know it diverges. And in fact, by the way, I could use direct comparison test, but I'll focus, use a limit comparison test. All right, against the p equals 1/2 series. Excuse me. So here we go. Take the given term, divide by the compared series term, 1 over root n. Take the limit as n goes to infinity. So what I do is I multiply the top and bottom by square root of n, gives me this. And then I divide I guess I divided by the square root of n, the top and denominator and numerator. They gave me this, but that of course goes to 0. I got 1 over 1 minus 0, which gives me 1. Aha! So by limit comparison test, the given series diverges, because we have limit comparison with c equals to 1. All right. To the limit comparison with c equals 1 to the p equals 1/2 divergent series. All right. Here's another example. Example 4. 1 over n times e to the 1 over n. We can compare that to the divergent p equals 1 series. So I take the limit of the term of the given series, divide by 1 over n, and that just leaves me with the 1 over n's cancel. I get e to the 1 over n, which is e to the 0, which is 1, right? So notice that this limit converges to 1, which then means that the given series S diverges by limit comparison against the p equals 1 series. All right? So here I've used this idea, label the series you're studying the convergence of divergence by S, so then you can refer to it later. Right? Again, please do not use the word it here. Use a label for your series or the series explicitly. All right? Thank you. Example 5. Here we have the sum n equals 1 to infinity of 2 over root n plus 2. And I think I'm doing a direct comparison to, limit comparison to the p equals 1/2 series. So I get that works out to 1/2. Thus, S diverges by limit comparison with p equals 1/2 series compared to S. Hey, this is a rerun. This is my example 3 was already like this. Oh well. This could happen, you know. So example 6. 1 over n to the n. Oh my goodness. What on earth is that? 1 over n to the n. That sounds unpleasant. So let's see here. So if you look at it, it's something that's smaller than the p equals 1/2 series. So that suggests to me that I could compare against p equals 2 and maybe I'll have success. So let's see if it works out. Oh, actually, I didn't do that. I mean, I did that directly. I just decided, well, I'm going to use the direct comparison test, because for n greater than or equal to 2, we have 1 over n to the n is less than 1 over n squared, but I know that 1 over n squared series for 1 over n squared is the p equals 2 series, which converges, so that follows then that sum n equals 1 to infinity of 1 over n to the n converges by direct comparison to the p equals 2 series. So we could, changing gears here a bit, you have options. We could either use direct comparison or limit comparison. In this case, I found direct comparison to be more convenient. Oh, here's the alternative option. Yowzers. Here we go. Limit comparison looks like this here. So if I do limit comparison for this 1 over n to the n sum series, then I face this limit, which gives me the limit as n goes to infinity of n to the 2 minus n. And so this is in indeterminate form, infinity to the, looks like minus infinity. So you don't know if that's going to work out to infinity or to 0. It's indeterminate. So the way I resolve indeterminate powers is to look at the exponential of the log of the thing. Then, since the logarithm is a continuous, I can pull the limit out. And properties of logs gives me that. Let's see here. How did that? Oh, when I pull it out directly, I get 2 minus n times log of n. But then bringing it to the denominator gives me log n over 1 over 2 minus n. What? Hey. Well, I don't think this is right. So we found an error in the solution here, guys. So the limit as n goes to infinity of log n is infinity. And the limit as n goes to infinity of 1 over 2 minus n is 0. This is infinity over 0. In fact, minus infinity over, let me think about this. As n goes to minus infinity, this is a, so you actually have minus infinity over a small negative. I think this just diverges to infinity. Well, let me just take a second here, guys. So, sorry about this. So this, just intuitively speaking, would be limit as n goes to infinity of n squared over n to the n, right? And if I were to, for purposes of brevity, just apply L'Hopital's rule, type infinity over infinity 2 times, it's not entirely pleasant because I got to learn how to differentiate n to the n to do the denominator. All right, but I've been through it before, and I can tell you what happens is the end to the n differentiates to something that still's got an n to the n in it. And, well, long story short, this is going to go to the limit of something like 2 over, it's too complicated for me to write here, but something that will blow up to infinity, so this limits to 0, I believe. In other words, if I'd done this properly, I would have seen that the limit comparison test does not apply. Now, I have tricked myself in this solution, right? So this step right here, this is a good example in some sense of, L'Hopital's rule is, only as good as it's applicable. And here I have, the type I have here at the start is infinity over 0. So this is not a L'Hopital's rule problem. So basically this down here is just junk, all right? So anyway, so whether you make my error or whether you calculate the limit correctly and get 0, either way, limit comparison doesn't help you for that example. But the different way we could fix it is to try limit comparison against something else. So I do limit comparison to 1 over 2 to the n. Then I've got limit as n goes, I want to think about limit n goes to infinity of this quotient, which gives me n over 2 to the n. And hopefully I can do this one right. Exponential of n natural log n over 2, which gives me log n over 2 over 1 over n. And then I said L'Hopital's, oh no, have I done it again? As n goes to infinity, that goes to infinity, that goes, oh man, I tell you what, I'm just out to lunch on this particular solution sheet. I'm sorry guys, that's just bogus right there, nonsense, junk. Alright, oh man, let's see here. Instead, well, yeah, so this is, goodness gracious. This is just, so you're looking at n times natural log of n over 2 as n goes to infinity. So n goes to infinity, of course. Natural log of n over 2 as n goes to infinity also goes to infinity. So you get infinity times infinity. Infinity times infinity as a form is not indeterminate, it just blows up. So we're looking at an exponential, something large. This thing just diverges to infinity as well. Alright, so sorry about that, guys. So there you go. Example 7, hopefully I will recover. So here we have 1 over n factorial. And so that's 1 over, so that's 1 plus a half plus a sixth plus a 24th plus a 120th and so forth and so on. And I said, well, we can compare this to the p equals 2 series. Because if you're looking past, this point, you're going to have something that's smaller, right? And so if we can show something, there's something larger because the fractions are, the denominators are larger. All right, so you can see that n squared is less than n factorial for n greater than or equal to 4. It's easy to see. I say it's harder to prove. So it could be proved by induction, perhaps. All right. Well, here's, so n equals 4. We get 16 is less than 24. Suppose inductively that n squared is less than n factorial for some n greater than or equal to 4. I made some misstep I had to white out. And then, I'm like, oh, okay, well then, n plus 1 factorial is equal to n plus 1 times n factorial, which is, by the induction step, greater than n plus 1 times n squared, which, by the way, is greater than n plus 1 times n plus 1, because n squared is greater than n plus 1. I will explain that more, I think, below. So I have that n plus 1 is greater than, n plus 1 factorial is greater than n squared. And that's the induction step. So proving that n plus 1 factorial is greater than n plus 1 squared would be the induction step, because that's what I assumed deductively, was that n factorial was greater than n squared for n greater than or equal to 4. So if I can show that for n plus 1, then by proof by mathematical induction, I've shown it's true for all n. So I'm like the thing that needs more attention that's not entirely obvious is why n squared is greater than n plus 1 for n being larger than or equal to 4. And so I give arguments for that down here. N squared is let's see here. What do I say? I said for n greater than or equal to 4, n squared greater than n plus 1 is clear. Since n squared greater than n plus 1 is equivalent to n squared minus n minus 1 greater than 0, which is equivalent to n minus 1/2 squared minus 3/4 greater than 0. And you can check that that is true for n greater than or equal to 4. I think that's, if we put in 4, what do we got? 4 minus 1/2, which is what? 7/2 squared, which is 49 over 4, right? Which is, of course, greater than 3/4, which is positive. And if we go beyond 4, that just gets better. So this is clearly true. And so this being clearly true means that that's true, means that that's true, means that my argument for the induction step was true. Now, there might well be a cleaner argument than the one I'm giving here, but it's an argument. So we conclude by proof by mathematical induction that n squared is less than n factorial for all n greater than or equal to 4. So all of this argument here just to prove that the direct comparison to p equals 2 series is reasonable for 1 over n factorial. All right. So getting back to it, we can observe that 1 over n squared is convergent p equals 2 series, and thus the sum n equals 4 to infinity of 1 over n factorial converges by direct comparison. Since 1 over n factorial is less than 1 over n squared, thus it follows that the sum n equals 1 to infinity of 1 over n factorial converges. If you can show the tail converges, you add a few terms to get the rest of the series, and you still get convergence, right? Okay. And then next up, we have examples of alternating series, but I'll stop this video and start the next one.